I want now to have a section 4 on the holonomy groups SUM and SPM, which are two of the cases in Berger's classification of holonomy groups. So we'll start with a section 4.1 on Calabi-Yau manifolds. So let's have a definition. This is our definition. So for us, a Calabi-Yau manifold is a compact Kähler manifold X and J and G with the complex dimension of X is M, such that the holonomy group of the metric G is strictly equal to SU of M. Okay, so that's the definition I'm using today. There are several non-equivalent definitions of Calabi-Yau manifolds available in the literature. I've chosen this one because this is a course on holonomy groups. So we can think about them as metrics with this particular holonomy group. So Calabi-Yau manifolds are usually compact, or they're usually defined to be compact, but people also talk about local Calabi-Yau manifolds, by which they mean certain non-compact Calabi-Yau manifolds, usually with asymptotic conditions at infinity. Also, sometimes people don't require Ricci flat, or they just talk about the complex manifold as being a Calabi-Yau manifold without a choice of Kähler metric. Sometimes you have a contained in SUM. Sometimes you require Ricci flat, but you don't require a holonomy group contained in SUM, so on. So there's different definitions around. But this is they're all some variations on this broadly. Well, any Calabi-Yau manifold is Ricci flat. And conversely, if X and J and G is a Ricci flat Kähler manifold, then the reduced holonomy group has hol 0 of G, so that's a connected component of the holonomy group of G containing the identity, at least contained in SU of M. So a general Ricci flat Kähler metric, the holonomy group itself need not be contained in SUM, but the holonomy group probably might be a finite extension of this thing, and the finite part could lie in the kind of U1 part of UM rather than the SUM part of UM. Okay, so, well, there are simple sufficient conditions for when a Ricci flat Kähler manifold is Calabi-Yau. So we have, using the Calabi conjecture, we have a means of producing examples of Ricci flat Kähler manifolds. So we find a complex manifold with first Chern class 0, and then Calabi conjecture tells us that we get these Ricci-flat calorimetrics. So we might want to know, are such things Calabi-Yau or not? And so, for example, here's one result you can prove. Let's have stated as a proposition. So let's suppose that X and J is a compact complex manifold with well, firstly, let's require pi 1 of x is 1. So that is the fundamental group is 1. It's simply connected. That's a global topological condition. And so in algebraic geometry kind of notation, Kx is Ox. This means that the canonical bundle is trivial as a holomorphic line bundle. And I'm going to prescribe some of the Dolbeau groups. Hp, 0 of x d bar is either C or 0. It's C if P is 0 or M, which is the complex dimension of x, and it's 0 otherwise. Okay, so that's a condition on the underlying topological space. These are conditions on the complex manifold only. So they're things you could verify using algebraic geometry. So then C1 of x equals 0. That follows from this triviality of the canonical bundle. So by the Calabi conjecture, or by the corollary to the Calabi conjecture, every Kähler class on X. Of course, these conditions don't actually imply there are any Kähler classes, but if you have a Kähler class, if there are Kähler metrics on X, every Kähler class on X contains a unique Ricci-flat Kähler metric. G. And the conclusion is that then the holonomy group of G is strictly equal to SUM. So therefore X and J and G is a Calabi-Yau manifold. Okay, so if M is even, then the conditions in this proposition are actually also... So I've given you some sufficient conditions for when you can produce Calabi-Yau manifolds with holonomy group strictly equal to SUM. If the dimension little m is even, these are also necessary. Okay, well, so the issue here is around about what the fundamental group does. For Calabi-Yau even, because of some argument to do with A roof genuses and characteristic classes, you have to have simply connected, and then the rest of the thing is kind of fairly easily necessary. For Calabi-Yau odd, it's possible to have finite at least Calabi-Yau odd dimension greater than 1. You can have finite fundamental groups, not just simply connected. And in the finite fundamental group case, you need some slightly more complicated conditions to make sure you get holonomy SUM rather than something smaller. Okay. Well, I'm trying to. For example, if you had SUM1 cross SUM2. If you were to take the product of two Calabi-Yau manifolds of lower dimension, then you get HP0 is C or 0, let's say if n1 is not equal to m2. In that case, you get HP0 of C is P is 0, m1, m2, or m1 plus m2, or 0 otherwise. So the Dolbeault cohomology condition is excluding these product cases. It also excludes SPM, which will give you HP0 is C or 0 in the case in which P is even, odd. Yeah, so basically this conditional Dolbeault cohomology excludes the other possible Halomny groups which you might have had for Ricci flat Kähler manifolds. Okay. So note that G is given by the Calabi conjecture and is not known explicitly. And it's basically never known explicitly in any interesting case. So it's not known explicitly in any examples at all for m strictly greater than 1. Okay, so in case m equals 1 case is T2, then you have a flat metric. It's just the metric on the Euclidean metric on R2 divided by translations. That's kind of trivial. For these kind of strictly Calabi-Yau manifolds, compact Halomny SUM, there's no formulae known at all for any Calabi-Yau metric. And I think that's kind of necessary. My expectation is that the Calabi-Yau metrics are transcendental. They aren't algebraic in any meaningful sense. Sorry. So, well, we can use complex algebraic geometry to find many examples of compact and complex manifolds X and J satisfying the conditions of the proposition. And thus many Calabi-Yau manifolds. So far, in any one dimension, we only know finitely many actual manifolds carrying Calabi-Yau structures, and any one of those manifolds would have a finite dimensional family of complex structures and metrics. So it's an open problem whether there can be infinitely many topologically distinct Calabi-Yau manifolds in any one dimension. My guess would be no, but that's basically unknown. So just as an example, if we let X upper M be a smooth hypersurface in the sense of algebraic geometry, a smooth hypersurface of degree m plus 2 in the complex projective space CP m plus 1. So this is defined by the vanishing of a homogeneous polynomial of degree m plus 2 in the projective coordinates of CP m plus 1. So for example, we could take X is the set of Z0 up to Z m plus 1 in CP m plus 1 such that Z0 to the m plus 2 plus dot 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 plus Z m plus 1 to the m plus 2 equals 0. So then C1 of x equals 0. This is done using this is a very simple calculation using something called the adjunction formula in algebraic geometry, and therefore x has Ricci flat metrics which are Calabi-Yau. So for example, if m equals 3, this is a quintic, which is a very famous example of a Calabi-Yau threefold. And this combination of complex algebraic geometry, which is a way of producing lots of examples, and the Calabi conjecture gives you loads of examples, basically. Okay, well, so here are some facts. It is known that so firstly, in dimension 1, complex dimension, m equals 1, every Calabi-Yau one-fold is, well, if you assume connectedness, is a torus T2 with a flat metric. So that's boring, you can just understand them very explicitly. Secondly, when m equals 2, all Calabi-Yau two-folds are K3 surfaces. Well, so the definition of K3 surfaces comes from the classification of complex surfaces, which is a kind of triumph of 19th century, early 20th century mathematics. And they're all diffeomorphic. So there's a single underlying real four manifold, and actually there's a connected family of complex structures and Calabi-Yau structures on that single four manifold. And the family of Calabi-Yau structures is described by the Torelli theorem. So, well, as I said, you can't actually write down the metrics on the K3 surface explicitly, but despite that, you can be very, very explicit as to what's going on. Well, basically, you can understand the set of periods. So every Calabi-Yau two-fold has got a Kähler class, which is a de Rham-Kerr-Moggi class. It also has a holomorphic two-form. And that has a de Rham-Kerr-Moggi class, and you can write down the family of triples of the Kerr-Moggi classes of the Kähler-4 class and the real and imaginary parts of the holomorphic two-form in de Rham-Kerr-Moggi very explicitly, and then you can show that basically you can you understand the family in a very, very, very nice way. So in this case, you can understand about everything you could hope to understand very, very clearly, except for being able to write down the metrics themselves. Okay, so in m greater than or equal to 3, all Calabi-Yau m-folds are, if you consider them as complex manifolds, are projective. That is, they are complex submanifolds of CPN for some large enough m. So that's proved by something called the Kodaira embedding theorem. I know to be able to do this, you need to understand something about the two-dimensional or the degree 2 cohomology of your Calabi-Yau manifold. It's important that you want that h2, 0 of x is 0. Okay, so if h2, that's not true in the Calabi-Yau twofold case because there's the canonical bundle section of the canonical bundle gives you non-zero pieces here. But for Calabi-Yau m-folds, when m is at least 3, you have h2, 0 of x is 0, because on a Ricci flat Kähler metric, anything in here would turn out to be constant and would reduce the Coulombic group. If you know this, then you know the whole of the cohomologies of type 1,1, and then you can use something called the Kodaira embedding theorem to show that the underlying complex manifold is projective. Okay, so therefore, for m at least 3, all Calabi-Yau manifolds come from complex algebraic geometry, and so we can basically, you kind of reduce the question to, the complex algebraic geometers get to own Calabi-Yau manifolds. We just say that understanding Calabi-Yau manifolds is much the same as understanding the underlying complex algebraic objects, which is an algebraic problem. So next I want to talk a little bit about string theory and mirror symmetry. I think I'm not going to make notes on the board on this. I'm just going to waffle mostly because there's too much to say. So Calabi-Yau manifolds are tremendously important in an area of physics called string theory. Okay, so Calabi-Yau manifolds, particularly when in dimension m equals 3, they're a kind of huge subject. It's a kind of industry which seems to employ thousands of mathematicians and physicists. So one reason for this is that there is an area of physics called string theory, which, at least according to the advertising, is aiming to combine quantum theory and general relativity, which are kind of two areas of physics which have been in tension for 100 years. Okay, so string theorists, at least in one version of string theory, say that the dimension of the universe is not 4, that is not the kind of 3 space-time dimensions and 1 time dimension that we observe. They say that it's 10. And the 10 is split as 4 plus 6, where these are the kind of macroscopic dimensions of 3 space plus time, and this, then the 6 dimensions, is some small Calabi-Yau threefold. Well, initially this is just a compact Riemannian 6 manifold, but string theorists want the theory to have a supersymmetry. And as far as I can tell, when you translate supersymmetry from physics into mathematics, it means you want a constant spinor. Okay, so it's a Riemannian manifold which is spin, and there's a spinor which is constant under the spin connection. And then it turns out that, so this is Riemannian 6 manifold with a constant spinor. So the subgroup of spin 6 preserving a spinor is SU3. So we end up with holonomy SU3, or possibly a holonomy contained in SU3. And this small Calabi-Yau threefold is supposed to have diameter of order the Planck length, which is 10 to the minus 33 centimeters. So that's so tiny that there's no prospect of actually probing it using experiments. And anyway, somehow the quantum theory has kind of fuzzed out all the geometry by then. Somehow the actual spatial stuff here is kind of not there anyway. But because of this, so string theorists are tremendously interested in Calabi-Yau three manifolds as kind of ingredients that you need to bake your universe. So now string theorists also expect that every Calabi-Yau 3 manifold should have a quantization. Okay, so quantization is some kind of a theory, which would be called a super-conformal field theory. And as far as I know, this is not really defined. Even if it was defined, the process of going from a Calabi-Yau threefold to a superconformal field theory would involve Feynman path integrals over huge infinite dimensional spaces, and those certainly aren't defined in any mathematically rigorous way. So there's a kind of big black box here, but going between Calabi-Yau threes and superconformal field theories. Now the physicists can do reasoning over here in some kind of heuristic ways, and they use that to make predictions about what happens to on the Calabi-Yau 3 side. And initially these predictions appear to mathematicians to be ridiculous. Okay, so one of the big areas is something called mirror symmetry. Which broadly is some kind of one-to-one correspondence between pairs of Calabi-Yau threefolds x and x hat. Okay, so this is already oversimplified, but this is some mysterious quantum relation between pairs of Calabi-Yau threefolds, which is supposed to, and broadly it's supposed to exchange the kind of odd dimensional geometry of one Calabi-Yau 3 with the even dimensional geometry of the other Calabi-Yau 3. It's supposed to exchange the complex geometry over here with the symplectic geometry over here. It's supposed to swap round the HPQs with the H3 minus PQs, the Hodge numbers. And okay, so initially, from the mathematical point of view, this is a bit like saying, well, I want a one-to-one correspondence between giraffes and bananas. Okay, it's apparently you're expecting people to relate to apparently very different things, but it does now appear to be true. So some major milestones would be Candelas, De La Ossa, Green, and Parkes in the early 90s. So they computed the Gromov-Witten invariance of the quintic using mirror symmetry. Okay, so that is the Gromov-Witten invariance. They're things counting numbers which somehow count the numbers of curves in your Calabi-Yau threefold. You translate it through this mirror thing, and it turns out that something difficult on one side can be correspond to something easy on the other side. So they went through this translation. They got to something called the variation of Hodge structure, which you can compute on the other side. They predicted these numbers of Gromov-Witten invariance. At the time, Gromov-Witten invariants were not defined mathematically, but nonetheless this was very interesting. And then eventually Gromov-Witten invariants were defined, and their computation was verified. And it's kind of amazing that they got the right answer, because there were at least 100 places in their calculation where they could have inserted a mistake and they didn't. Another milestone is due to Kontsevich in 1994 in his ICM address, homological mirror symmetry. So this says that if you've got a mirror pair like this, broadly, what you want is an equivalence of triangulated categories between the derived category of coherent sheaves on X and the derived category of the Fukaya category. So derived Fukaya category. Here, this is derived category of coherent sheaves. So this is something which depends upon the complex geometry, or the complex algebraic geometry of one side of the picture. This is something which depends upon the symplectic geometry of the other side of the picture. And you have to do complex geometry and symplectic geometry have a rather different character, apparently. Complex geometry is very rigid, symplectic geometry is very flexible. But if you do something weird to both sides, this process of taking a derived category, then you can form two things called triangulated categories, which have the same kind of structure, and the claim is that these should be equivalent as triangulated categories. And again, this is a massive field, and it is verified in a lot of cases. For example, for the K3 surface and for the quintic, some version of this equivalence has been proved by people like Paul Seidel, Nick Sheridan. So again, this seems to be true. So, okay, that's kind of about all I've got time to talk about, but you should be aware that these Calabi-Yau manifolds is kind of really massive area with all kinds of interesting stuff going on. And the Calabi conjecture is just one tiny part of the whole story. Okay, so next I want to say something about the hyperkähler, the Holmby group's SPM. And I haven't got much time for that, but so we'll have a section 4.2 on hyperkähler manifolds. Okay, well, so let's talk about the quaternions. H, these are an R algebra. So H is the span of 1, I1, I2, I3, satisfying I1 squared is I2 squared is I3 squared is minus 1, I1, I2 is minus I2, I1 is I3, and so on. And, well, there is an S2 family of embeddings of algebras from the complex numbers into the quaternions by, well, for all triples A1, A2, A3 in R3 with A1 squared plus A2 squared plus A3 squared is 1. You can map C into H by 1 maps to 1 and I maps to A1 I1 plus A2 I2 plus A3 I3. So whenever you're dealing with the quaternions, there's always this two-sphere of ways of being complex, really. So let's consider the quaternion vector space H to the m, which is R to the 4m, as a left H module. So it's basically a vector space over the quaternions. Because the quaternions are not commutative, you have to distinguish between left actions and right actions. I'm going to have this acting on the left with the Euclidean metric So if I think about elements of this as column vectors of quaternions, well, mod squared of that is just mod of q1 squared plus up to mod of qm squared. And then the group of symmetries of h to the m as a left h module, and let's say g0 is sp of m. Okay. And you think about these as elements of FBM can be A, which is an m by m quaternionic matrix with A bar transpose is the identity. This is a possible Holmby group of Riemannian manifolds. So a manifold X 4M with Riemannian metric G with holonomy group of G contained in SPM. Well, it has complex structures big I1 and big I2 and big I3 corresponding to the complex structures little I1, I2, I3 on your model vector space H to the M, with big I1, big I2 is equal to big I3 as using kind of multiplication on tangent spaces. And then actually, well, A1, I1 plus A2, I2 plus A3, I3 is also a complex structure for all A1, A2, A3 in the two-sphere S2. And G, the metric G is scalar with respect to this complex structure A1, I1 plus A2, I2 plus A3, I3 for all points in the two spheres. So a hyperkähler manifold is scalar with respect to not just one complex structure, but a whole two-sphere worth of complex structures. So that's where the name hyperkähler comes from. It's scalar in a whole family of different ways. So hence, G is scalar with respect to a whole family, whole S2 families of complex structures and is called hyperkähler. Okay. Well, so we have SP of M is contained in SU of 2M by identifying H to the M with C to the 2M, let's say using the complex structure I1. And well, SP1 equals SU2, but it's a strict inclusion for M greater than 1. So, well, in the lowest dimension, so therefore, Calabi-Yau two-folds are the kind of first examples of both Calabi-Yau manifolds and hyperkähler manifolds. But really, Calabi-Yau two-folds, they kind of behave more like hyperkähler manifolds than like Calabi-Yau manifolds. So it's kind of better to consider Calabi-Yau two-folds, which in the compact case are K3 surfaces, as being the kind of avatars of hyperkähler things than of Calabi-Yau things in higher dimensions. So let's talk about the compact case. So that there aren't very many compact hyperkähler manifolds known. Okay. Well, you can construct compact hyperkähler manifolds by, well, first constructing the complex manifold X, I1 for just one of the complex structures, or if you prefer, you can construct X and then A1, I1 plus A2, I2 plus A3, I3. Construct the complex manifold using algebraic geometry. and then using the Calabi conjecture. That's just because of this inclusion, hyperkähler manifolds are Ricci flat. So if you find an appropriate complex manifold, well, let's say compact complex manifold, then you'll get Ricci flat Kähler metrics, and under suitable conditions on the complex manifold, these will be hyperkähler. Unfortunately, there are hardly any examples known. Well, I'll leave that out. Okay, but basically, very few examples are known. Basically, well, for all m greater to 2, there are 2 examples. You can use the Hilbert schemes of m points on K3, or the Hilbert scheme of m plus 1 points on T4 divided by T4, acting as a group of translations. And then there's also 2 kind of extra examples in dimensions, real dimensions 12 and 20, due to O'Grady. So they're basically much more difficult to find than Calabi-Yau manifolds for various reasons. So O'Grady's examples, almost everything in this subject is somehow to do with K3 or T4. So K3 and T4 are the 2 Calabi-Yau or 2 kind of hyperkähler manifolds in dimension 2. So you can produce moduli spaces of coherent sheaves on K3 surface. These Hilbert schemes are special examples of those. Mostly those turn out to be singular. These particular ones are non-singular. So O'Grady found some extra examples of moduli of coherent sheaves on K3 surfaces which could be desingularized to give you something hyperkähler. But okay, there's all kinds of other ways of thinking of clever ways of constructing hyperkähler manifolds, and you do that and you get to the end of your calculation, and then you find that they're deformation equivalent to one of these, basically. And there's lots of rather nice geometry about non-compact hyperkähler manifolds. So again, as in the Calabi-Yau case, the compact hyperkähler manifolds, they're pretty much non-algebraic. Well, the entire hyperkähler structure is kind of non-algebraic. But although some special complex structures will generally be algebraic. For non-compact hyperkähler manifolds, there's lots and lots of nice families of non-compact hyperkähler manifolds which are completely algebraic and omit very explicit descriptions. So there's a kind of a nice area of things of geometry studying non-compact hyperkähler manifolds. There's things like quotient constructions. So there's a quotient construction for symplectic manifolds which allows you to reduce dimensions of symplectic manifolds, Kähler manifolds, by dividing by a group. There's a hyperkähler version of that story where you can, if you've got a group of dimension dim G acting on a hyperkähler manifold, you can make a new hyperkähler manifold of dimension reduced by 4 times the dimension of G, and so on. Okay, but that's all I've really got time to say about hyperkähler manifolds, unless you want to ask about them.